Well, you didn't have to be a psychic to know that this was coming. Now we're going to look at how forces act at angles. All right, so here's a pretty typical situation. I've got a wagon or some other wheeled thing with low friction, and I'm applying a tension force that's not in the direction of motion, but at some upward angle, in this case 30 degrees. And I'm going to go ahead and tell you that the applied force here, the tension force, is 20 newtons. So what happens then is if I want to resolve how the motion of this object is going to respond to these forces, I've got to break these forces like I've done before into a component that is basically parallel to this, the horizontal force, and then the vertical force. Now, we'll see later on that won't necessarily always be horizontal and vertical, but for right now it is. So if this is my angle, the adjacent angle is going to be found by taking the cosine of this times the force. So 20 cosine 30, I know that the horizontal component of force is 17.3 newtons, and that the vertical lifting component of the force is going to be found by using the sine of this angle. So 20 sine 30 gives me 10 newtons of upward force. If I was asked how fast would the wagon accelerate, well, it turns out this vertical component of force is at right angles to its motion, so it's not going to cause an acceleration. What is going to cause an acceleration, however, is going to be one that's acting in the direction of motion. So I'm going to take this value here to try to solve for the acceleration of the cart. So F equals ma. Some of the forces do, but there's only one force that's going to cause motion. So I can put 17.3 newtons here, 8 kilograms here, and when I solve for it, I get is 2.16 meters per second. That's the rate at which this would accelerate in this circumstance. Now, if I tip this angle upwards, then there'd be a smaller horizontal component, and the object would accelerate at a slower rate. And conversely, if I tipped it downwards, I'd get a smaller angle here, so more of it would be horizontal, it would accelerate faster. Now let's take the wheels off the cart and talk about friction. So here's a kind of interesting thing. So up till now, when we've talked about friction, we've talked about the normal force. It's usually been just equal to mg, right? You have an 8 kilogram mass sitting on a floor. It's being pulled down with an mg of 80, so the force pushing up with a normal force of 80. But not anymore, because a proportion of this, 10 newtons of it, is lifting upwards. So I'm using the same forces, 20 newtons at 30. So the upward component, 20 sine 30, is 10 newtons. So I'm lifting up with 10 newtons. So I'm still pulling it sideways here. So it's in motion. So I want to know how much frictional forces, kinetic frictional force, is there resisting the motion of this object. So I'm going to do a free body diagram here. Now, in this free body diagram, I'm only showing mg. I'm not showing the applied force here. I'll get to that in a minute. I'm just looking at to try to figure out what's going on in terms of the normal force. So what I find here is I've got mg down as 80. And since the object is not accelerating downwards or upwards, I know that the net of the sum of the vertical forces has to sum to 0. So therefore, if this is negative 80, then this must be positive 20. Positive 10. So this must be equal to positive 70, because 70 plus 10, the upward forces have to equal the 80 of downwards. Why is this important in this case? Because if you recall, the equation for finding kinetic friction is equal to mu times the normal force. Static friction would be frictional force is less than or equal to mu times normal force. But here you go. In this case, the normal force is not mg. It's basically mg minus 10. So what I get here is the force here is going to be the normal force is going to be equal to 70 newtons. So when I solve this, I'm going to get 14 newtons rather than the 16 newtons I would have got if I hadn't lifted up on it. Of course, that's going to allow it to accelerate faster horizontally too, because there's less resistive force. We'll do that when we get into activities rather than in the screencast. Okay, well, this might look a little bit spooky at first, but you'll get used to these. Okay, so here what I've got is this. I've got two tension forces, T1 and T2. Here they are. All right. And I'm told that the tension force is 100 newtons in both cases. And I see that they're both acting at a 30-degree angle to hold up mass m. If I want to know what the value of mass m is based on this information, how would I solve that? Well, I'd say, well, let's think of this. Mass m pulling downwards with mg. So therefore, there must be a net mg total upwards, right? So the net upward component of these two tension forces has to sum to mg down. So what I would do then is I'd say, all right, let's see what component of this 100 newtons is lifting up for this one here. And what I'll find is 100 times the sine of 30 gives me 50 newtons for this one, and 100 times the sine of 30 gives me an upward of 50 newtons from this one. So the sum of these two is 50 plus 50. So 50 plus 50 upward minus mg downwards is equal to ma, but a is 0 in this case, so it equals to 0. So all I'm doing is saying sum of the forces equals ma, and since a is 0, ma is 0. So then I can just say, well, that's 100. I can move this one over here and just call it mg. I know that g is 10, so if I divide this side by 10, I can see that m equals 10 kilograms. So the trick here is to know that the component that was upwards was the sine of this one because it was opposite from this angle, and also that I had two of them, so they summed together. All right, but we don't always have two of them. So let's look at another case here. All right, you'll probably see something like this on the test. This is a pretty common setup here. So I basically have a mass, in this case I'm told it's 4 kilogram, and I have two tension forces. T1 is a string that's acting at 90 degrees, pulling it towards the wall this way, and I have T2, which is at 60 degrees here. And I'm asked to determine, based on just this alone, what are the values of T1 and T2. Now, here's how you do this. There's some things I know. First of all, I know the system's not accelerating, so that the sum of the forces has to add up to 0. So first thing I'll say is I know what mg is. Mg is 40 and it's directed this way, and it's not accelerating this way. So therefore, there must be a total of 40 newtons in the upper direction. Furthermore, I know this cannot be contributing to this because it's at 90 degrees. So it's not lifting up at all. So that means it's only T2 that's lifting up. So I know then that that I have an angle of 60, and that the sine of T2 times the sine of 60 is going to equal 40. So if I say T2 sine 60 equals 40 and solve for T2, I get 46.19 newtons. Now I know what this tension force is. Now that I know that, I can tackle this one here. Now, I have to know this one first because I had no information about horizontal, but now I do, because now I know that this one here is equal to 46.19 newtons. And furthermore, I know that there is a component of this force that's acting this way that's counter to the one acting this way. So the tension force this way and the component of this tension force this way must be equal to each other because the object does not accelerate in the horizontal direction. So therefore, all I had to say is 46.19, and this would be the cosine uh, times the cosine of 60 is going to give me this. So 40.19 cosine of 60, I see this is 21.1 newtons. All right? So it's all predicated on the idea that the object is not accelerating. Last thing, and we'll be done. This is a short one. Okay, so one thing that's worth pointing out is this. When I have a diagram like this and I'm asked to draw a free body diagram for it, College Board is very picky about the fact that they do not want you to draw component forces on a free body diagram, only actual forces acting on the object. And sometimes it can be a little bit frustrating for you. But the idea is I can't do this. This tensional force is acting at a 45-degree angle, and it's got a value of 40. I can't just say, well, therefore, t sine 40, t sine 45 gives me this, and t cosine gives me this, and put them all at right angles. I wish we could, but we can't. Instead, what you had to do is show the actual forces. So what I know then is uh, that I have 5 newtons of frictional force. I was told that. I can tell from this that I have 40 newtons of mg. I'm told from this that I have 40 newtons of tensional force in this direction here. Now, what I'd have to do, though, is I would have to go ahead and figure out what is the normal force by taking the sine of 45 and multiplying it by 40, and that gives me 28.28. And then I have to take that away from 40, because if I'm lifting up, if this tension force is lifting up with this much force, how hard is the floor pushing? What's the actual normal force? and there it'd be 11.7. So I put that one here. I had to put the actual normal force. That's a little bit frustrating. So here, these three were given to me. I had to use this information to find this one, but I don't draw the component forces. I draw the actual tension. So this is a real force. The string is doing this. This is a real force. Gravity's doing this. This is a real force. Friction is doing this, and this is a real force. The floor is doing this. This and this are not real forces. Okay, thank you for watching this. We'll see you tomorrow.